Happy start of week 4. Is it already week 4? I believe it is. So we're going to get started on the wave picture and talking a little bit more about interference. We're going to finish off polarization today, and we're going to try and survive the wet and blustery. It's blustery. That's what it is. It's blustery. It's a wet and blustery day here on the central coast of California. So I hope you all are safe and warm and wonderful and enjoyed a weekend full of peaceful something or others or whatever it is that you hope for. A couple of things. So we'll do for PLC 4 this week. I will post that a little bit later today, but it will be up and running and ready to get going. And as usual, that will be for Friday. In the usual quiz style format. And we have homework 2 already out. Homework 2 is going. It's posted, and after today and a little bit of tomorrow, most of the problems will likely make a little bit more sense. Okay, so I'm looking for next Tuesday on the due date for that. And as usual, there will be a quiz on that day. Other than that, I don't think we have anything else planned. So what we'll do is get started with the polarization. I was talking to you a little bit about the picket fence picture, and we'll go from there. So the picket fence idea is the analogy to polarization, where you have a set of basically absorbers, long absorbers, and a wave can pass through them if it's kind of lined up with them, right? So something that would go through here would be vibrating like this and would be able to go through, but something that's going this way, right? Oh dear, it hits total failure. Everything explodes. Well, it just gets absorbed. So as nice as that picture is, it's simply good for analogy's sake. All right. So the actual mechanism is not quite that, but nonetheless, for a visualization technique, the picket fence idea is pretty good as a representation of the Polaroid filter, okay? So speaking a little bit more of polarization, I want to introduce you to the math representation of it, okay? Because the like I've been saying, so if you have a wave that's going this way, right, it will pass through, but a wave going, let's see if I can draw it properly, this way, will hit and get absorbed. That one passes, this one's absorbed, or blocked, however you like to think of it. Okay, so generally, this is not 100% true, but generally, light is unpolarized, right? That's probably true for most of the light you see, certainly not all of it, but most of it, what you're seeing is that light is unpolarized, which means that you can represent it as a set of arrows, which generally, wow, the wind is really blowing. Which generally looks something like this, something that vibrates that way and something that vibrates that way, right? So unpolarized light, you can think of it as doing that, and then I can say it's traveling this way at whatever speed it's going, right? So this is the speed v here, and these are indicative of the fact that the polarization axis is both of those. So you're getting both sets. Now, if I use a Polaroid filter on this, I would be cutting how much? Well, if you think that the light could be vibrating up, down, left, right, and there's really no preference. In other words, if you look at light from a light bulb or a light fixture, this is generally unpolarized light. And when I use a filter, right, a filter is basically a set of picket fences. I can push that filter around and have it pass or block different parts of the polarized wave, or the unpolarized wave. And if I have unpolarized light, how much am I blocking? I'm probably blocking half of it, because there's no preference that the light has, whether it says, oh, I'm going to be polarized this way versus this way. I mean, there's no there's no preference to it. Okay? It doesn't make a choice like that. It just is basically half of it's this way and half of it's that way. So if I hold a filter up here, I'm blocking half of it. All right, so imagine that I have a filter. I'll just draw a nice round filter here like that. And let's suppose that it's oriented like so, such that its pickets are vertical, like the picket fence is in this drawing here, like that. So visually, what we're going to do is we're going to say, well, it's going to pass the vertical one, right, as it comes through this one, and it's going to block the horizontal one. So if I denote that there is an incoming intensity, and I call that I naught, okay, suppose that's I naught. Whatever that intensity is, right? Intensity is a power per unit area. Okay, so it's an energy per time per area. And that falls on top of this thing. Then what do I get on the out part? Well, the horizontal piece is blocked, and so the vertical piece makes it through, and I get this. And it's still traveling at whatever speed it's going. I'm assuming that's C, but I'll just put V here for whatever reason. Okay, like so. All right, now I can also have it go through another filter here, but maybe this filter is a little bit slanted. Instead of being directly up and down, maybe this filter is a little bit more like this. Suppose it's at 45 degrees or something like that. Make it easy, whatever angle it is. Okay, we'll just denote that there's an angle here. So I'll extend this thing here, and I'll take a vertical piece here, and I'll say that there's an angle to that Polaroid, which is away from the vertical. All right, so it's cranked over at, like, if I'm looking at it from the point of view of the incoming light, it's over at, like, say 10 o'clock. Right? Instead of being directly up at noon, it's over at 10, and it's kind of pointing 10. It's pointing 10 and 4 on the clock face. So it goes into that. Now, what do I expect to be on the outside when I come out? When I consider the light that's emerging here, what am I expecting to get out here? Okay, so that's the part of it here that we want to address. Now here, all right, so this is half of it is blocked here. So the intensity here is equal to 1/2 I naught at that stage. All right. Therefore, and that's a general rule. If you have a Polaroid filter and unpolarized light, it doesn't matter which way you orient the Polaroid, you're blocking half the light. Okay, because no matter what you do, you can always rotate the axes of polarization. I can always just rotate them like this, and whichever way I rotate the Polaroid, it's blocking half of it. Right? So this is not going to go very well. But if you look through the darker part of this, the only, not this part, but the polar. If I just rotate this, you'll see, if I just hold it over here, you'll see that writing, it gets a little bit, but that's because I'm getting some, whoops, here. I'm getting a little bit of reflection off something else. But if I just turn this, it doesn't seem to change what you're seeing behind here, right? It doesn't change the brightness of that lettering. Perhaps if I hold it like this, okay, and I say, look, I put another Polaroid in its place. I rotate this front Polaroid like so, that's basically the same. You can't really tell a difference from one to the next because once it goes through this one and they're parallel, if it goes through this one, it's already going that way. So if the polarized light is parallel with the Polaroid axis, you get 100% transmission. Okay, but if it's at crossed, if they're at right angles to one another, let's put that back here. If they're at right angles to one another, like you would see here, they're at right angles to one another, I get a zero transmission. Okay, so the question is, what kind of mathematical function is maximum when things are parallel and minimum or zero when things are at right angles? And you might pick the cosine. And I think that's a fair thing to pick. So if you think of the angle at which the Polaroid is slanted compared to the incoming polarized light, then we're going to deal with a cosine piece that does get transmitted. Okay, so this is the general, I call this the 1/2 rule. Just that half, if it's unpolarized light, okay, it's got to be unpolarized, but if it's unpolarized light and there's a Polaroid, it's half. And that's pretty much always true. But the thing that sometimes trips people up is that sometimes it's not unpolarized light. This is already polarized. This light is already polarized. Only when I have something like this, which is vibrating in both directions, do I have unpolarized light. And by the way, it's doing it equally. Okay, do I have unpolarized light? So, and doing equally and randomly. So when I get here, I have polarized light, and it's now trying to pass through a filter. How much do I get? Well, I call this the cosine rule. Really, it's the cosine squared rule, so I'm going to put cosine squared like that. It's the cosine squared rule because because reasons. Technically, you don't have to have had 4B prior to taking this class, so I don't want to belabor the issue, but you have an electric field vector, you have a magnetic field vector, like I mentioned last time, and the electric field vector is the one that we choose to represent the polarization. So if the E field is vibrating in one direction, you have a vector that way, and if I have a Polaroid that's slanted with respect to that, then how much makes it through is dependent on the transmission of the electric field, but the intensity is related to the electric field by a square, so we have to square it. All right, so the cosine squared rule is that polarized incoming, or let's say incident polarized light, is reduced by a factor of the cosine squared of the angle between the polarization of the light and the Polaroid axis of the filter. Incident polarized light is reduced by cosine squared theta, where theta is the angle made between the polarized axis of the light and the Polaroid axis of the filter. Between light's polarization and filter's axis. Okay. All right, so in this case here, if this was a 45-degree angle, then you would take the cosine squared of 45 degrees, and that's what would be over here, which, by the way, would be a half, because it's squared. So here you'd get something out that looked like this. How do I want to draw it? Coming out parallel with the filter, and now the intensity over here is equal to what it was to start with times the cosine squared. So if I'm following this through, and if I'm chaining this through, then I would take this intensity here and multiply by cosine squared. Let me write that a little bit bigger down here so we can see it a little better. Like so. Okay, just squeeze that on there, okay? So if you're chaining, in other words, if there are multiple Polaroids, right, there's multiple polarized filters that you're going to chase light through, you just use these two rules, okay? If it's initially unpolarized, it goes through the first filter, half. It goes through the second filter, cosine squared theta. It goes through a third filter, cosine squared theta. All right, so let's do a quick example on this. And those are really the only two rules to worry about when it comes to polarization. So let's take this same situation here. Let's take the same situation here and let's just pass light through a couple of different ones. Let's suppose that I have I'm going to have unpolarized light incoming. Okay, I'm going to have unpolarized light incoming here like this. And I'm going to just pop a chain of filters on here. So I'm going to have one filter here, which say is going to be like this. That angle theta. I'm going to have another one here. Let's see. Interesting. We're going to do this one here, so that's going to look like this. Let's suppose that from there to here, same angle. I'm going to do one more here. I'm going to do this one. Like so. All right, so I'm going to have three filters. The first filter and the third filter are the same. In other words, I've tilted it the same amount off the top by this angle theta. All right, so these first filter and third filter are the same filter. The second one is the same filter again, but I've turned it such that the angle, it's the same angle theta, such that the angle is now measured up from the bottom this way. So it's like, instead of pointing like these ones are pointing at about 2 o'clock, this one's pointing at about 4 o'clock, okay? So I got unpolarized light coming through. I've got an unpolarized light coming through a 2 o'clock filter, passing through a 4 o'clock filter, and then passing again through a 2 o'clock filter. All right? So let's take a look at what do we expect to be the outgoing intensity when we get down here. All right. Okay, so let's take a look. We're just going to assess the intensity at every stage. So here I have starting intensity of I naught. And so when it passes through the first filter, yeah, it's rotated over, but so what? I could just consider my axes to be rotated over that way and it comes through, so half of it goes through. All right, so I'm going to call I naught the starting. We're going to have I1 through the first filter, I2 through the second filter, and we're going to find I3 out here. The way you do this is to multiply successive intensity changes. Okay, so what we're going to find is that I1 should equal 1/2 I naught. All right. Now, when I look at the light coming through filter 1 here, it's going to be polarized with the filter. Okay. Now I'm going to pass it through another filter, and that filter is oriented at what angle relative to the first one? Okay. Well, it's the same angle from the top as it is from the bottom. So I have to just figure out how much is that angle. All right. So with respect to that, what I'm going to have here is that it is coming through at this angle like that, right? So the polarization axis of the light has rotated to be parallel with this filter here, and now it's trying to pass through this one. So if I think about how I measured this axis, then what I'm going to have is a theta here and a theta there. So I'm going to get a, let's see, if I go down to there, I'm going to get 90 minus theta. And then if I go all the way here, I'm going to go 90, but I don't want that. I want 90 minus theta twice, basically, is what it looks like. So if I go like this, oh, whoops. I need to plug in my computer real quick. All right. Okay, sorry about that. Just had to plug in my computer. Okay, so by the time I get from, where was I? I was starting here. And so I got to go from here. And if I went straight out at 90 degrees, then this angle would be 90 minus theta. Okay. And the angle here, from there to there, would also be 90 minus theta. So the question is, what's the relative angle from filter 1 to filter 2? Okay, so it looks to me like it's two 90 minus thetas. Okay, in other words, the light started off coming out of filter 1 polarized this way, and filter 2 is trying to polarize it that way, which means the light has to rotate, or it's going to pick out the component that is rotating through that angle there and then that angle there. Okay, so for example, if theta was, say, like 50 degrees, okay, say something like 50 degrees, well, then the angle between here and here would be 80 degrees, right? 40 for the complement here, 40 for the complement there, and that would be 80 degrees total. All right, so the second one, I2, is equal to I1 times the cosine squared of 90 minus theta. Sorry, 2 times 90 minus theta. I just got done saying that and I already forgot. Of 2 times 90 minus theta. Like that? Okay. And now, once again, it's going to pass through the first filter, a copy of the first filter. Sorry, not the literal first filter, a copy of the first filter, which is then going to rotate the polarization axis of the light back up the way it was. So it's going to be this again. So I3 is going to equal I2 multiplied by exactly that same factor. 2 times 90 minus theta. Okay, so like I said, if this was 50, if theta was a 50-degree angle, then I lose half the light coming through the first filter no matter what the angle. I come into the second filter. After I pass the second filter, I lose a cosine squared of 80 degrees, right? A 40 plus a 40. And now I got to shift it back up going through the third filter, which is 40 plus 40 again. That's another cosine squared of 80 degrees. So I'm actually going to get a cosine to the fourth when I multiply all this stuff together. All right, so when I do this, the total outgoing polarization relative to the incident intensity, total I3, is equal to, well, I2, which was that. So I'm going to multiply this thing. I'm going to multiply all of this times that. That's going to be I1. But I1 is half of I naught. So I'm going to get half of I naught times cosine squared of this times cosine squared of the same thing again. So in this case, I get cosine to the fourth of 2 times 90 minus theta. And like I said, if theta was, say, 50 degrees or something like that, I'd have cosine to the fourth of 80 degrees here, which would mean I really cut the light down quite a bit, because at 90 degrees, I would have blocked it completely. Yeah? All right. So the takeaway points here are the 1/2 rule for unpolarized light, the cosine squared rule for polarized light, and then when you have a number of filters like this, you just multiply all the polarizations as they go through. Easy peasy. Okay. Lots of really cool applications of polarization. One of them is in the recent, I don't know if recent's the right word, but there's always been 3D movies around. The reason you have a 3D movie is because the projectors are playing two different polarized light films on top of each other, and they give you those glasses and they're polarized slightly differently, so that one eye is seeing one thing and one eye is seeing a slightly different thing, and your brain stitches it together to give it depth perception. So it's pretty cool. 3D movies, not possible without polarization. All right, there you go on that. I got one other thing I want to talk about before we get to the main topic of today. And what I want to talk about then is the radiation pressure. And this also involves the intensity of light. Okay, and this is possibly a strange thing to consider, and it takes a little time to maybe get used to this, but it is a foot into our next model, which is the photon model. However, what we're going to do is we're going to say, for now, we're just thinking about waves, and we're going to say, okay, let's consider the momentum that light carries. Okay, light carries energy. I don't think anyone's going to disagree with that. But it also carries momentum. And that momentum acts kind of like a 4A momentum. In other words, it acts like a thrown baseball. All right. So first part here to consider is that light carries momentum. And it carries what kind of momentum? Well, I'm talking about the linear momentum. It turns out there's other things that it can carry too, but we're just going to talk about this for now. Light carries linear momentum, P. If you remember this from 4A, the quantity P equals mv, right? But that's a classical definition, and so it's not going to work here for light. This is classical. Okay, light is most definitely not a classical object. Um, however, I am talking about that momentum, and the same thing will be true that we found in 4A when we looked at collisions between things that carry momentum and things that either carry a different momentum or carry no momentum. So, for example, suppose that you were going to catch a baseball, or say you wanted to know the force that you would have to that you would have to apply to a baseball in order to catch it and stop it. Okay, so just let's try a bit of recall here. Catching a baseball. It's the first thing I think about here. So here comes the baseball. It has some speed v to it, some velocity v if you like, and your hand is, maybe you've got your glove on, right? And you're going to catch the thing. It's coming in with some speed, and then the last piece is, okay, it's come to rest inside your mitt here. Okay, so you have your mitt, which is, right, got the big thing there, and you've caught the ball, and velocity, say 0. Okay, and the question is, how much force did I have to, so there's a collision here, and the final picture is that. So the question is, how much force did I have to apply in order to stop the ball in some small amount of time? Well, you would have had to have applied a force which was basically equal to the time rate of change of the momentum, according to Newton's second law. Newton's second law tells us that the force applied is equal to dp dt. And by the way, this is the sum of external forces, just so I don't get any flack on that one. That's the sum of the external forces equal to dp dt. And that's Newton's second law as he originally wrote it. So the force you have to apply basically then is how much momentum did you have to take away from the ball in what time interval. All right, so this is basically going to be approximately the same thing as delta p of the ball divided by delta t. Okay, and we know what that was, mv and all that stuff. Great, so we can calculate that. Okay, now I want to compare that to the case where the ball hits your glove and bounces back. Okay, so instead of coming in and getting caught and stopping, now let's compare this to the situation where the ball comes to your glove and you try to go for it, but you miss it and it hits you and bounces back. And let's just assume it bounces back at the same speed, but whatever you like. Okay, let's suppose that it does that. Let's suppose now that I'm going to imagine the situation in which the ball is traveling that way at speed v, and you're trying to catch it, but instead of catching it, let's got some hand drawing classes here. Okay, like that. Let's suppose that as you bring your hand towards it, it hits and bounces off. And let's just suppose it bounces off and goes backwards at the same speed. Now, what force did I exert on the baseball? Well, in the previous case here, how much did I reduce the momentum? Well, I reduced the momentum from its original value down to 0, right? So really, the change in the momentum of the ball was the momentum of the ball. Right? Because the delta means initial, it means final minus initial, and the initial is whatever it is, momentum m times v, and the final is 0. All right? So I'm just going to ignore minus signs, whatever, it doesn't matter. The minus just tells you that you're pointing the force opposite the direction of the momentum. Okay, but the magnitude of the force is approximately something like how much momentum did the ball have divided by the time. Now, what's the case over here? What now is delta P if I look at this situation over here? Well, here I had a momentum going that way, and now I've got a momentum going that way. It's really, really tempting to say, oh, they add to zero and they cancel each other. But that can't be right. That would tell you you have zero force applied when the ball clearly changed direction and is now going this way. So in this case, the net force applied is approximately 2 times the momentum of the ball divided by delta t. Because not only did you take away all of the incoming momentum that was pointed this way, I took that all away, and then I gave it momentum going this way, if you think of it that way, right? That's what the force did. And therefore, the change in the momentum of the ball is really take this one away, give it that one, and those two effects add. So the total force is actually twice the momentum of the ball divided by the time. Now, why are we going through all this? Because what I'm about to do is stop talking about baseballs and start talking about light. Suppose that we have light incoming to something like a surface that's going to absorb it. Right? Here comes your light. It's coming into a dark, like a surface here, and that surface is, I don't know, black colored, right? It's going to go in there and it's going to get absorbed. Now there's going to be no light left. What do? Well, if you have that on a small wire, you'll find that it pushes, the absorption of the light actually pushes on the black surface here, and it pushes the wire because the light is absorbed, and that means it gave up its momentum just exactly like you had to catch the baseball, and it did so to the tune of a kind of like a force, but a force with an area involved. Okay. Wow. Just got a sudden big gust of wind out there, and it's knocking stuff over. Well, try to remember, stay out of the way of moving stuff. Be safe out there, folks. Try not to catch stuff that's moving that has such big momentum. It's not going to work for you. So the momentum that we're talking about is the momentum with the momentum that the light has. So the question you might have is, well, how do we calculate what the momentum of the light is? Well, it's kind of related to the intensity, okay? So the light is, it has some intensity here, and you've basically taken it all away by absorbing the light. So what we do is we say there's a pressure exerted, literally a force exerted on an area, okay? So the radiation pressure exerted, in this case, is the intensity of the light when it started here, call that I, right? It's intensity divided by C, which is its speed, okay? So why does that come in? Well, because I'm skipping a few steps here. Instead of talking about force, here I'm talking about pressure. And going from momentum to intensity, there's a few things in there. So I'm just going to kind of get to the chase. In this case, the radiation pressure here, right? The kind of the point of this particular argument was that if I had incoming light like this, what does it do in this case? Basically, it hits a mirror and it reflects and comes straight back like so, right? So this is a mirror in which some of the light has been reflected. Well, in this case, all of the light's been reflected, and the same exact relationship holds that this is now twice the intensity divided by light speed, c. Okay? So this is a real phenomenon. And in fact, NASA has for many years considered a solar sail In other words, a spacecraft that's powered by a um, a piece of curved, shiny metal, such that the sunlight hits it, bounces off, and pushes the metal this way. And all you got to do is attach a satellite to it or a spacecraft to it, and off it goes. Right? Basically, propelled by a constant force, which speeds it up. Well, it's not quite going to be constant because of the intensity decreasing, but it's a pretty good push most of the way, and it's going to be free and does not need any. The spacecraft would not need to carry any propellant with it, which is a pretty nice thing. Kind of on the par with the solar powered cars. If you see those, they have solar powered car competitions every year. Okay, so what I want to do here is calculate. I thought what might be kind of fun is to calculate what's the force exerted by the sunlight hitting Earth and pushing it, because there's a pressure exerted, right, by this sunlight that's hitting stuff. Well, how big is that? We've got Earth. Earth is pretty big. So how much force is the sunlight exerting on Earth? And then let's compare that to just to get a feel for how big that is. Let's compare it to the gravitational force that sun exerts. So the force of sunlight on Earth, force of sunlight on Earth. Okay, let's assume that Earth, let's just make an easy assumption here. Let's just assume Earth is absorbing it. All right, so it's really an intensity divided by C issue. Here at Earth's surface, the solar constant is what the name of this thing is. The sunlight has a particular intensity. And this is a pretty nice number to know off the top of your head. Sunlight intensity is approximately it's a little over a kilowatt per square meter. It's actually about 1.4. And it doesn't really matter if you know the 0.4. Kilowatts per square meter. So that's about a little over 1,000 watts. That's 1,400 watts in a square meter area, right? That's pretty big. So that's like 1,400 watt incandescent light bulbs in a 1 square meter area. And if it's really bright and sunny, yeah, I could see that, right? Well, it doesn't always bright and sunny. It's not really what we have out there right now. But nonetheless, we are getting something. And so you can consider this an average. Okay, it's approximately equal to that. So what are we going to do? We're going to say, well, the sun is here and Earth is here. And what's happening is that sunlight is hitting Earth. And let's just assume that it's getting absorbed, okay? Let's just assume absorption. Let's assume absorption. So that means that the radiation pressure is equal to I divided by C. And if we wanted the total force, then I'd need to multiply by the area over which that pressure is exerted. And we could just consider that more or less approximately the surface area of Earth, but only half of it, right? So the total force is then pressure multiplying area, and that's going to be I times A divided by C, where A is half of surface area of Earth. Okay. The surface area of Earth is, I guess, 4 pi r squared, so half of that, 2 pi r squared. But really, it's just a circle. I don't like that. Let's not do that. Let's do it's about a circle. Let's make it about a circle. Half. So let's make it circular. Because half of it. Well, I guess that's. No, I'm all right with that. Forget it. I changed my mind yet again. Let's just say half. I'm okay with that. It's coming in approximately. The sun's big enough where it's coming in approximately hitting the poles like that. Yeah, all right. Well, it's only approximate anyways. Let's just keep it at a half and see how we do. So this is going to be equal to 2 pi r squared, 2 pi of radius Earth squared, multiplying I divided by C. So if we just calculate that number out, let's just have a look at what that number looks like. All right, so the total force due to sunlight is then 2 pi radius Earth squared times the intensity divided by C. And so 2 pi we know. Radius of Earth is in meters, it's about 6.4 times 10 to the 6. Let's just call it 6 times 10 to the 6 meters. That's going to be squared. The intensity is about 1,400 watts per square meter. And now we're going to divide all that by 3 times 10 to the 8 meters per second. Okay, so if we do that, let's just make a quick analysis of what we got here. I got a number that's 6 squared here is 3.6, and that's going to be times 10 to the 13th, which is going to get killed off with about 5 of those, or leave 5 of those when I kill the 8 off here. 5, but I'm going to get an extra factor of 3 from the 1,000 here. And that's 3.6 times 2 pi, which is again about 6-ish, and that's another 1.4. So you're really talking about 5, 8, 9. You're talking about a number that's in the range of about 10 to the 8 or 10 to the 9 newtons. Okay, I'm just going to say it's approximately 10 to the 9 newtons. A billion newtons. Doesn't that seem like a lot? It does seem like a lot, but that's to us. We're not a planet. We're not planets, thank goodness. So just to put that number into perspective, compare that to the size of the sun and its gravitational force on Earth. This is, for me, some of the fun part of doing physics. Just approximations and then meaningful comparisons. Compare that to the sun's gravitational force, which is in the order of, let me see here, about 10 to the 22. 10 to the 22 newtons. So, okay, it's actually not really that big. 10 to the 9th is big, but 10 to the 22, I'm not a mathematician, but I think that's a lot bigger. There you go. Anyways, okay, so that's radiation pressure. Radiation pressure is a real thing that light carries momentum and can push things based on the area that you put in front of them, put in front of the sunlight, and it will provide a force to you basically at no cost, which is pretty cool if you want to launch stuff out. All right, the main topic for today and therefore the rest of the week is interference. And it's the interference of waves because that's what we're talking about with the focus on light, right? So interference. What is interference? Well, interference is a situation of two lights, or should I say two waves, meeting each other at a point in space. All right? If you've ever looked at ocean waves, then you will have seen this type of thing, right? When an ocean wave hits a rock that's in the ocean and then interferes with if there's another rock nearby, right? The pattern that it makes. If you've ever dipped your finger into a glass of water or dipped 2 fingers into a glass of water, right? Then you're looking at wave interference. Okay. Um, One of the other ones that I always notice, just because I'm that kind of person, driving over 17 when you get to Summit Road, there's a set of bars on either side of the overpass at Summit Road. There's bars like that. But if you approach them from this direction, the spacing between these looks a little bit bigger than the spacing between these. And so you get actually an interference pattern. You'd notice this also too if you have two screens behind each other. And you look at it like this and you can see there's this funny pattern of light and how the light and dark bits of the screens look to each other. So that's what interference is. It's the meeting of two waves at a point in space and then trying to determine what happens. All right. Interference basically, and it doesn't matter the wave. So it's two waves meeting at a point in space. And the question then is, okay, what happens? Do they add to each other? Do they take away from each other? What do they do? Okay. So I want to show you here something that's pretty interesting because this is light and people would think, oh, well, light is always there. And when you add intensities, it always comes out to be brighter, right? Well, I want to show you this here. Let's see if I got this the right way around. I want to show you this here. Come on, oops. Come on. All right. Hopefully we got a laser. Yep. Okay, we got a laser beam here on the board. Handy dandy laser. And in between, now right here where the laser is, I have this thing here. And if I show that to you here, laser's being emitted from right here. Can't quite see that, but it's right down in the bottom left of the screen. Laser's being emitted there. In front of that, I'm going to put this thing here, which is just a set of two scratches on a piece of photographic film, and the scratches are really close together. Okay, so I'm going to put this in front of it, like that, and now it's on blink. I don't want it on blink. Stop blinking. That is not what we want. Okay, there we go. Nope, it's back to blinking again. What the heck? Try again. Huh. Oh well, I guess you get blinking. All right. Let's see if you can see this. Let's see if we can get it slightly. Let's get this one here. If you can get this pattern, probably it's going to be hard for you to see, but you'll see, I don't know why the blinking is happening, sorry. You'll see that there's a, a central maximum right here. I'm looking at my screen right now, and I don't think you can see, I don't think you can pick up, there's actually more brightness on the outsides, out here and out here. So I got a bright fringe there, I got a bright fringe there, one there, one there. And it would be great if we could see that, but I don't think that you can. Oh well. You have to take my word for that one, I guess. When two light waves meet at a point in space, they can interfere. Light actually was hitting every single point along there, but some places it was adding and making the light brighter, and in some places it was adding to make the light dimmer. All right, so basically when we talk about superposition, which is a word that you may or may not be familiar with, but the word superposition is basically adding the effects of successive things, right? So if I have a wave and it's hitting here, I'm going to take that wave's effect and then I'm going to add this other wave's effect. I'm just going to add it right on top of it. I'm superposing the effects. That's what superposition means. It's not like a really awesome position. It just means that you're superposing things. You're adding things on top of other things, right? So this is essentially adding the effects. I like to think of it now. You all are probably not old enough to remember transparency projectors. These were wonderful things. Just they're around still. Every now and again, you'll see someone using them, but really bright. There's like a light in a box which basically projects by mirrors up onto the screen on the board here, and then you can have a little 8.5 by 11 piece of plastic, which is transparent, and you can write on that and then erase it just exactly like a whiteboard, and then the people can see it because it's up on the screen. So if I took a transparent piece and I had something on it and I put another transparent piece on top of it, I am superposing those two things, right? That's what superposition means. Okay, so let's examine this. Let's examine what happens when we look at light waves hitting a point in space. Okay, suppose I have a point in space here and I got a light wave coming this way, and it hits that point in space at one of its peaks, and I got a light wave coming in this way, and it also hits at one of its peaks. All right? That would be, if I'm going to do this visually, like when we did third grade math, you would have something like this adding to something like this. Okay, not very well drawn, but notice the peaks line up, the troughs line up, the peaks line up, the troughs line up, kind of. The peaks line up. All right, so what do I get when I add that wave on top of that wave? Well, I should get a wave with bigger peaks and deeper valleys, right? So it should look, but the frequency, the wavelength, right, is still the same. So it should look more like this. Like that, right? Where the amplitude of this wave is, say, 1 and 2. The amplitude of this is 1 plus 2. Okay. If, however, and now the rain starts, blustery. If, however, I get a lining up which does not occur peak to peak, but instead peak to valley, what if I get a situation like this, and I'm adding to it a situation like this? Now what do I get? Notice I have the peak, it's lined up with the trough. This trough is lined up with the peak. This peak is lined up with that trough, right? This means I get a nothing if these amplitudes are the same size. Okay, if I had the peak bigger and then the trough was a little bit, yes, I'd get a little bit of a wave through there, but let's suppose that they're the same size. So I would get nothing. I'm just going to write a 0 there. If 1 equals 2, and all I did was just shift them a little bit. Okay. All right, so the question is, how do we get interference? By what method does interference happen? Well, let's take a look. There's basically 3 ways that we're going to examine on how to get interference. Number 1, we're going to look at a wave, and I'm going to compare that with a wave that travels through a material in which its wavelength is reduced. All right, so if the wave is going to travel through a material with an index, then its wavelength is going to be reduced. So imagine that if I had a wave and it had a wavelength like that, and now I'm going to add to that a wave that looks like this, right? I may not get them coming out at the exact same point in their waves. In fact, that one's coming out at the top, that one's coming out near the bottom. I might get kind of destruction here, right? They might kind of destroy each other. This is, by the way, this situation here when you get very low signal on the adding, that's called destructive. That's called destructive. Whereas the other one that I erased right here was called constructive. So this would be a type of interference because the wavelengths have changed slightly. Well, in this case, they've changed by a lot, but if I change the wavelength, then I'm going to have the wave going through more cycles, and by the time it comes away from the material, it won't be likely at the same point in its cycle as the one that missed the material, right? So if I'm comparing one that's missing a material to one that's going through a material, and here they come. Okay, where are they? Right? At what point in the wave is that one? At what point in the wave is that one? And that's how we assess what kind of interference has happened. All right, so wave traveling through material with index n, we find that if a wave travels further, like a further distance than another one, then we find that they're going to come to a point and again not be at the same place in their cycles. One wave travels further than another. And this last one here is that one wave bounces off a boundary. The boundary reflects it, okay? And when undergoing a bounce off a boundary, we find that the phase shifts by 180 degrees. So we'll say that one of the waves reflects off something. And then the phase shift is 180 degrees. All right. So of all of these, I think the easiest one to tackle is this one here, where the one wave travels a little further than another. And let's try and diagram out what that looks like. In the context of the demo that I tried to show you, but we had a lot of blinkiness going on, and also that the effect was small enough that you couldn't really probably see it very well. In that context, let's examine light coming out of two slits that are very close to each other, and then looking at what kind of pattern we're going to get on a screen. Okay? This is known as the double slit experiment for obvious reasons. And I will exaggerate the sizes of the slits here, and I'll exaggerate the angles at which we're going to talk about this, but when it comes to light, this is a fairly small setup. right? In other words, the distance between these is on the order of maybe 1/10 of a millimeter, possibly 1/100th of a millimeter, okay? And the screen length is probably on the order of a meter or more. So we're talking about this being a really, really small distance compared to what I'm about to show you here. This is kind of like what I drew here with the sun and earth. They're way out of proportion. Okay, so imagine I got a screen here. Okay, this is 2 slits. This is a screen, and I'm catching the light on the screen. I'm shining light back here. Right? I'm shining light back here. In it comes like this. Okay, obviously a lot of these arrows are going to get blocked because I have only a couple of places where light can get through. So let's examine light getting through real quick and coming through and going straight. That's an easy situation. Light comes in from here and here and goes straight. Oops, kind of bends a little bit apparently, like that. And it meets right there. Okay, so notice that the point on my screen here is halfway between the 2 slits. Would you think that it's fair to say that both of the waves here traveled the exact same distance? And by the way, I know I'm not drawing waves, I'm just drawing the rays right now. But the waves traveled the exact same distance from leaving here or here to arriving at the screen, right? Yeah. So if they travel the exact same distance, then they go through the same number of wavelengths, which means that they should be adding in phase the entire time. So that should be a bright spot, because by light, if you have an amplitude adding to another amplitude, that means brightness. Okay. Now, suppose that I pick a different spot on the screen. I'm going to pick a spot up here, and I'm going to look at this distance there, and I'm going to say, how much different is that distance from this distance? There. Can you see those are definitely different distances? So the question is, if one of them traveled further than the other, by how many wavelengths did that wave travel above the other one? Yeah? So if, for example, the bottom wave, which travels further, if the bottom wave travels a full 1 wavelength more than the top wave, you see that when it's going like this wave, the bottom wave down here is going to go, and it's going to be ready to go, and then they're going to swim together. And they're going to be there, and it's going to be all great and wonderful, and they're going to add constructively, because they'll be at the same place in their cycles. But if the bottom wave traveled only a half a wavelength more, then what you've got is, right, now this one's on the up, that one's on the down, and it goes the rest of the way, and they reach that point, and they are out of phase completely. If that's happening, then that's a dark spot where light has met on that screen. Okay? So what it comes down to is how much further did one of these waves travel than the other one? And that's known as the path length difference. So let's say that here. How much further does one wave travel than the other? Okay, that is known as the path length difference. The path length difference here, maybe you can kind of see it. If I drop a perpendicular straight down here, and I make this triangle that's right here that I'm going to shade in, so maybe you can see it a little bit better. The bottom leg of that triangle, this piece right here, this piece right here is basically how much further the bottom leg traveled than the other one, because by then, they were both here, and by then, they both went the same distance, right? So if I just figure out how much of a distance that is, and then I compare that to the wavelength, I'll say, okay, how many wavelengths fit into that distance? If I know that the number is 1, then I'm going to say, oh, that interference I can predict is going to be bright. If that number is 1/2, I'm going to say, oh, I can predict that interference is going to be dark. All right? So the question for this type of experiment is really, number one, how much further is the wave here traveling than the wave here? And then the next question is, and how many wavelengths fit into that distance? That's how you assess the interference that you see on the screen. So this is first question. Second question is, how many wavelengths fit in there? Okay, so if you can answer those two questions, then you will be able to predict what kind of interference you're going to see here on the screen. All right, so what we'll do, I think, is stop there, because I think I'm just about out of time. We'll pick this up tomorrow, and we'll do the analysis of this situation, and then we will probably get enough time to go through the first one of these here with the wavelength reduction, and then the wave reflection we'll probably talk about on Thursday, and we'll go from there. In the meantime, I will post the PLC. That'll be good for Friday. Homework 2 is up, so start getting a look at that. I can hear thunder outside. It is pouring rain and blustery, winds gusting pretty solidly here, so be safe out there. Have a great rest of your day, and I will see you tomorrow.